Good afternoon. This physics class today we'll be looking at a topic called dynamics. Dynamics. When you talk about dynamics, it simply has to do with the study of motion. You will agree with me that before we can talk about motion, something brought about the motion. So invariably, anytime we talk about motion, we cannot but talk about the force that brings about the motion. So this aspect called dynamics is an aspect of classical mechanics, okay, or what's simply called mechanics, so which has to do with, when you talk about mechanics, we can broadly divide it into kinematics and then dynamics, which of course today is our focus. But it's also very good that I talk about kinematics because sometimes we might want to cover up the aspect of force. That is, we are silent about the force that brings about the motion, but we are much more concerned about the effects, such as position, represented as x, for instance, in a particular direction, one dimensional. Or we talk about x dot, which is talking about the velocity. Okay, this dot A actually stands for the first derivative. So dx dt, and it is measured in meters per seconds, as you can see. So we can also go further and look at the second derivative of this, which we call x dot dot, but usually for a uniform motion. A non-uniform motion, for this case actually might look mathematically complex. So, but then we talk about motion under uniform acceleration. That is, at this level, what we look into. So, this same thing as, if this one is your V, that's the V, the T, okay? So, we same thing as the square X, the T square. So this one is measured in meters per second squared. So, like I said, that is kinematics. We are silent about the force that brings about the motion. So various other things we look at in this aspect includes projectile and several other things. So, but note very well that when we are dealing with motion without due regard to the force that brings about the motion, we are only simply dealing with kinematics. But that does not outdo the fact that it is force that brings about motion. So these are point of focus today, dynamics. So, and like I've simply described, dynamics has to do with the study of motion, because as regards even the force that brings about the motion. So essentially in these aspects, we are going to talk about Newton's law of motion, Isaac Newton. So who won a Nobel Prize, giving us three basic laws of motion. So let's consider that to understand what we mean. But before I go further also, let me say this. I said mechanics, okay, or what I simply call classical mechanics. When we deal with matter, as you know that physics, chemistry, and some other sciences, they deal with what? Matter. But in this case, talking about mechanics or classical mechanics, we are dealing with bulky matters. Bulky matters. What do I mean by bulky matters? Things actually that you can carry. Things actually that you can feel and touch. Okay? Bigger in size, such as what? Bench, table, ball, and so on and so forth. So we deal with them under what? Under classical mechanics. However, when it becomes so small, on a kind of nano scale, something actually that is not really visible to eyes, like atoms, things like electrons, protons, and several other atomic particles like that. So classical mechanics actually will not satisfy that. So we go into what we call quantum mechanics, right? So quantum mechanics deals with that. But like I said, this is classical mechanics under which we are dealing with dynamics. So very quickly, let's go to Newton's law of motion. So Isaac Newton uh, was able to give us three basic law that governs motion. First law, Newton's first law of motion. So another way we can call that what we call the law of inertia mass. In bracket, law of inertia mass. What does that mean? What that is simply telling us, let's assume that you have a ball. If you place the ball on the field, this law is telling us that that ball or that object will continue to stay at that position if there is no effect of a force on it, any external force acting on it. If the same ball is kicked by you, this law is telling us that that ball will continue to be in a state of motion. It will be moving infinitely. It will be going non-stop until there is a counteracting force that stops it. So this is what law of inertial mass is talking about. And another thing about law of inertial mass actually is a function of the mass of the object. What are we talking about? You've been able to differentiate between mass and weight. When you talk about mass, we are looking at the quantities of stuffs inside a particular matter. Okay, how much it contains. That's what makes up its mass. So, if an object is massive and then it is in motion, it becomes more difficult to stop it. Compare a car and a loaded, container. That is a lorry. You find out that it's easier to stop a car than it is to stop a loaded tanker or a trailer. So that is what law of inertial mass is telling you. And on the other way around, it's also easy for you to push a faulty car than for you to say you want to push a tanker, faulty one. So I don't know how many of you actually want to pull or push that one. So, but you understand what I'm talking about is that is what law of inertial mass is telling us. As long as a body is in a stationary position or is in a state of motion, it will continue to remain in that state except there is an external force acting on it. That is simply what law of inertial mass is talking about. Have you ever asked the reason why actually you have to use a seat belt? That's part of the safety measure. Because when you are in motion, you and the vehicle, you are all in motion. And so if for any reason the driver, hits the brake, then you also find out that that's when you realize that you're also in motion. So that is about law. So what does it state? It says that provided there is no external or counteracting force on an object in motion or in a state of rest, it continues to maintain that position. So that's in a way to illustrate that. So provided that there is no external force acting on an object in motion or in a state of rest, it continues to maintain that position where it is. So that is simply what law of inertial mass is talking about. Let's quickly look at Newton's second law of motion. Newton's second law of motion. Now, so we talk about rate of change of momentum. So here we introduce two new terms. So let me quickly mention, I've mentioned one already, momentum. Now, what is momentum? Momentum simply means the product of mass and its velocity. That is m times v. So m equals to mass, and then v is equal to velocity. All right? Okay? So invariably, so we can write the units as in Newton's seconds. Okay? So, or you can say that is kilogram meters per seconds. So, dimensionally, these are the units. So, what would we mean by momentum? Okay? Assuming you take a bouncing ball or ping pong, what we call table tennis ball. If you are hitting it against the wall, at every instance that it hits the wall, okay, there is an impact it has on the wall. So which is a function of its mass and then the velocity with which it hits the wall. So that's what we call momentum. Is that okay? So your velocity, that is the velocity you propagate it, and then the mass will determine the extent of impact it's going to have. So therefore, momentum has a twin brother. We call that impulse. Okay? So impulse is simply the product of force and then the time. It has the same units, Newton seconds, as momentum. So now, how do all this culminate into Newton's second law of motion? Newton's came again to tell us that the rate of change of momentum, that the force, exhibited by any particular body is a function of its rate of change of momentum, and it is always in the direction of that force. In a very simple mathematical way, we say that F is directly proportional to acceleration, where let's introduce mathematical constants. So that's equals to Ka. So where F equals to the force, which is in Newton, A equals to the acceleration, all right? So which is measured in meters per second squared, and K, which is some known, constant, which we'll soon find out, okay? So, but basically what Newton is telling you, this is what we call proportionality symbol. It's telling you that the rate, your force is directly proportional to the acceleration. So, and of course, your acceleration also will always be in the direction of the force. Don't forget, force is a vector quantity, just as acceleration it is. So, now, what is this known constant that we're talking about? It's a very simple thing. It's constant, and that is the same thing as your mass. So F is equal to ma. So that's how we define force. So that force is what? Product of mass and acceleration. But don't forget also that your acceleration, okay, but A is equal to what? dv dt. That is change in velocity over change in time, if it's decimally as we have. So then it follows that F now is equal to m dv dt, okay? But don't forget, dv dt is obtained from delta v, which is equal to what? Vf minus vi. Please note all of this. dv, that has to do with infinitesimal change in your velocity. Delta v has to do with your change in velocity over a certain range or limit or boundary value. Then the final velocity and then the initial velocity. That's simply your change. So I can as well write this and say F is equal to what? M delta V, okay? The same thing goes for this delta T. So and that's equal to M into bracket VF minus V high, okay? All over T for T high is equal to 0 because we are considering a body at rest. So the initial time is 0, then at time T, then that is the force. So therefore, it follows that M, into brackets V F minus V high. This will call your change in momentum. All right. So let P, okay, equals to M dV. Therefore, F now is equal to P all over T. So where P is equal to change in momentum, or let's say momentum. All right. So that is delta P. Let's look at that. So change in momentum. So this is what we have. So if that is taken, these are all derivations. So now that is what Newton's law of motion is telling us. Two things, don't forget again. It's regarding momentum as well as the impulse. And then some other terms that generate from this include the acceleration. Okay. So, and then the change in momentum as we have. So this is what Newton's second law of motion is telling us. But don't forget, this Newton's second law of motion actually is with regards to a single body, that is an object. So every derivation I've done here, I've considered it in relation to just what? A particular body moving in a well-defined axis or direction. So that is what we have. So now, but what about a case whereby actually we are considering the two body? Okay, then that comes in the Newton's third law of motion, and very soon we'll soon see the application and practical application and illustration from different examples. So we have this. So we say that Newton's third law, Newton's third law of motion. So we call it law of equal and opposite, action and then reaction. All right, what does that mean? What is telling us that for every action, there is a commensurate opposite reaction. All right? If I kick you, I believe that actually you won't want to maintain the same position. You may want to reply or want to respond. So in a way. So let's look at it that way. So Newton's third law of motion is simply what? The law of equal and opposite reaction. So what is it telling us? That we are considering two bodies. That if we have body A and then we have body B, okay? What it's telling us is that the amount of force that A operates on B is equal in magnitude but opposite in direction to that of B on A. I say it again. This, by understanding, is saying that when you have two bodies A and B, okay, the magnitude, the amount of the force that A applies on B is equal in magnitude, in size, but opposite in direction to B on A. What are we saying in essence? Don't fight with your friends. But if you have a friend and then maybe he offends you and then you slap your friend, don't forget, you that you slap someone, you also feel some pain. When you hit the wall, let's say with your palm, the wall will not only feel the impact, but you yourself also do what? You feel the same impact, to the extent to which you eat it. That is what this is illustrating. So let's consider another case. We have a chair and you sit down on this chair. Okay? Now, you sit down comfortably and then you are not afraid of falling down. Why? Don't forget, your own weight acts what? Vertically downward. So is the weight of any object. So the weight actually is unidirectional, always acting vertically downward through the center of gravity of anybody. So assuming yourself seated here, all right? Now, your weight acts downward. This is your weight. But then you are not afraid of falling down because there is a counteracting force that actually sets you in this equilibrium position. So that's what we call the reaction. So generated by the what? The feet, of this chair. So we have R, we have R. So usually we use R to denote what? The reaction. So what we are saying is that F, okay, let's say that's a vector, is equal but opposite in direction to what? Your R. So that is the reaction. All right? So that is what Newton's law of motion is talking about. So basically, we have looked at Newton's first law of motion, which has to do with what? With the mass, especially of an object, and what effect it has on its motion. Then the second Newton's law of motion that has to do with acceleration. So anytime you apply a force, you are producing what? Some acceleration. That's what we're saying. That is what we consider. So, and then including the third law, we have not only looked at just the body itself, but we have looked at two bodies simultaneously. And we have seen that the degree or the extent of a force or one object is equal and opposite to the effect of the other body on the initial one. So these are basic Newton's law of motion, what we call classical law of classical mechanics. So basically these three of them. So it works well as far as bulky bodies are concerned. As we soon find out later, this classical law actually begins to fail when we begin to look, into some nanoparticles, smaller particles like of atomic sizes. So let's quickly take a look at some questions and then we'll see how we can practically apply this. I have some practical questions here. So let's take a look at the very first one. The question says, what is the ratio of the weight of an astronaut on the moon to its weight on Earth? What is the ratio of the weight of an astronaut on the moon to its weight on Earth? So the G value was given. That's the acceleration due to gravity on Earth, 9.8 meters per second. And then on the moon, we have 1.6 meters per second. Now, this particular question is testing the understanding, of the relationship between weight and mass. You must be able to differentiate between the two. This is basic. Now, aside the fact that mass is measured in kilogram, which is the SI unit, and weight is measured in Newton, which is a form of force, other disparity between the two include the fact that weight, like I said, of any body acts always vertically downward. So like I said, weight is a form of force. W is measured in Newton, is equal to mass, which is in kilogram, times G, which is the acceleration due to gravity. So note this. This makes the difference between mass and weight, the acceleration due to gravity, which always acts vertically downward. Mass of any object is peculiar to that object. Like I said, it is the quantity of stuffs in a matter. That is what is simply mass is. You can compare a 40 leaves exercise book to your physics textbook. So when you look at that, in terms of the volume of pages, the difference is obvious. So that is how we can actually explain mass, the quantity of stuffs inside the matter. However, if the mass is kept constant, this G value can vary, all right? And it varies from point to point, even on the earth surface as well. So that is G, right? Because you find out that some places are close to the equator than some other ones. So you just like different. So G value. So now, what are we saying? In the moon, this is the value. On the earth, this is the value. So the only thing actually that can relate the two of them together is the mass of that object. So, and that's what the question is asking for. So let W1 equals to the mass on Earth and W2 equals to the mass, weight on Earth, and then W2 weight on the moon. So this is what I mean. Okay? Weight on the Earth, weight on the moon. The same value, W1 is equal to M. Note, is the same mass. So the mass is constant. Then times G subscript E. That's the gravitational force on Earth, or the acceleration on Earth. Then W2 is equal to mass times Gm. So which is the gravitational force on the moon. So therefore, let's call this one equation 1. Let's call this one equation 2. So from 1, we can make M the sort of formula. M is equal to what? If you divide both sides by G, W1 divided by M by GE is equal to M GE divided by what? GE. So therefore, GE is equal to what? W1 over GE. So similarly, okay, for equation 2, okay, we can have that. So GE, M is equal to GE over W. So then for equation 2, we can as well say that M is equal to what? W2 divided by G subscript M. So if, let's call this one equation 3, equation 4. So we can equate the two of them together, and then we can say that M is equal to W1 over GE equals to W2 over GM. So this represents the ratio. So then, now the ratio of the weight of the astronaut in the moon, so compare to that on the Earth. So what does that mean? So we can manipulate this equation and say that Gm over Ge is equal to W2 over W1, where W1, slash W2 slash W1 is the weight ratio of the man, of the astronaut, okay, on the moon, okay, to the Earth. All right? So that is as simple as that. So therefore, the ratio we are looking for, W over W1 now, is equal to, what is Gm? That is 1.6. And what is G? That's 9.8. So therefore, if you multiply this, so you find out that this here is 1, and this here, that is 8. So that is 1 over 8. So which is equivalent to 0.1, 25. So which is the ratio? Because it's a ratio, it is unitless. So therefore, that is the solution for question 1. So briefly, let's quickly look at question 2. So question 2 is a very simple case. A force of 20 Newton acts on a mass of 2 kg. What is the acceleration produced? So from the Newton second law of motion, we have that F, okay, is equal to what? Is equal to ma. So what are the parameters given here? We have the force, which you identify as in Newton. then you have your mass, which is in kg, and then you have A, which is in question. So, but whatever you want to do anything like this, ensure that your units are in SI units. They are SI unit form. Otherwise, you did conversion if it is necessary based on the taste of your examiner. Now, let's look at this. So, in this case, A, making A the sort of formula, we have A is equal to F over N. So, therefore, we have 20 Newton. This one is given as 2 kg divided by 20 kg, 20 Newton. So, this Newton here is kilogram meters per seconds squared. So, if you write it, so following dimension analysis, so then you have 2 here, 1, 2 here, that is 10. So kilogram cancel kilogram. Therefore, A is equal to 10 meters per second squared. So that solves the case. Here is another case. So now this actually is testing your understanding on Newton's second law of motion. So solution. The question says a lump of mud of mass 0.75 kilogram moving at 3 meters per second, hits a wall at right angles, okay, and stops dead. So find the impulse on the lump of mud. So, like I said in the first before, that momentum and impulse, they are brothers. So, for you to understand or to be able to solve this, you need to realize that, we said F is equal to m delta v over t, where this is your change in velocity and this is equivalent to m into bracket vf, okay, minus what? Minus v high. So vf is the final velocity and v high is equal to initial velocity. So we have a case of a body. Consider this to be your wall, all right? And then this is your lump of mud, okay? We are told that it's moving at right angles, okay, and stops there. So what does that mean? Actually, the motion is perpendicular to the wall. That's what it simply means. So it moves like this. So this motion is perpendicular. So now, what are the things you need to note? So let's call this one equation 1, okay? From 1, you realize that F times T is equal to M delta V is equal to M into brackets VF minus VI. Now, what does that mean? This body was moving with a constant initial velocity 3 meters per second square. But now, finally, it stops. So what does that mean? So this illustrates that while your VF is equal to 0, because that's your final velocity, okay, then your initial velocity VI is 3 meters per second. Is that okay? So note that all these quantities we are dealing with, they are vector quantities. And when you talk about vector, we give regards to both magnitude and direction. So direction is of utmost importance. It can make a lot of difference. So impulse, momentum, all of these are vector quantities. So now, what does that mean? So if everything is conserved, let's say, of course, usually momentum is always conserved, okay? That is the algebraic sum of your momentum, both and after the motion actually should be 0. Okay? And then, depending on the kind of collision you have, whether inelastic or inelastic, energy may or may not be conserved. So, but usually momentum is always conserved. So, and like I said, that means that the initial and the final momentum actually, they are the same. That's what that is saying. So, now in this context, so knowing fully well that this your Ft here actually relates to your what? A pulse. Is that okay? So the mass of the object has been given. So what does that mean? So just go ahead. Therefore, it follows that impulse, which is equal to what? Ft, which is equal to m into bracket Vf minus Vi, now is equal to what? Your mass. That's 0.75 kilogram. Is that okay? Then your Vf is your final velocity, which is what? Is 0 minus, what do you have? You have your initial velocity to be what? 3, everything in meters per second. So when you do so, 3, you have 0.75, okay, kg multiplied by 3 meters per second, because 0 minus 3, everything now is minus, note it. So 0 minus 3 is minus 3. So therefore, it follows that 3 times 5, that is 15, okay, that is 2.25, Newton seconds. So what does that tell you? This is very simple, that there is a reactional force. Your impulse is in the opposite direction to your what? To your motion. So that's why it shows that what? It is what? It is negative. That is what is expected. Is that clear? So impulse is the product of force and time. So, and as you can see, so this is the relation that connects them together. So this is your final answer, minus 2.25 newtons seconds.